Okay, hello everyone. I'm Ahmed Farid. I'm a fresh graduate from Zuel City of Science and Technology and Innovation. Our work here in this paper, we are using our paper here was made in undergrad work as part of our thesis graduation project. So basically, we are implementing an assistive solution for visually impaired individuals. That means we are combining the approaches of computer vision and sound synthesis, actually 3D sound synthesis, to provide a richer experience for the visually impaired while navigation. Okay, during our literature, we have observed, according to the World Health Organization, we have more than 2 billion visually impaired worldwide, causing more than 400 billion productivity loss. That means that there should be an assistive solution that can help them in their daily life and the navigation and doing everyday tasks. Okay, we surveyed the assistive technologies in the recent research and in the market. We have come to different 5 categories for the assistive technologies. Each category can serve and do much advantages and have its disadvantages. For the first category, we have visual imagery systems. Visual imagery systems mainly uses a camera as an input to their solution. They have higher accuracy, of course, but at the point of having more computational resources, not achieving real-time performance on most technologies, and also more cognitive load. What do we mean by cognitive load is that a lot of information can be perceived by the user, and that is not helpful in real-time performance. That causes the user to have a lot of distractions and can harden the process of navigation in the street. So for the second category, we have non-visual data systems. These systems uses sensory devices as the main input to their systems. Of course, it can achieve a real-time performance. However, they cannot go beyond basic obstacle detection. We need more information. We need more assistance to the visually impaired. For the third category, we have map-based systems. In these systems, they have pre-planned maps for indoor environments that can help the user navigate in these environments. For its disadvantages, it cannot work in new environments. So the user must have a pre-planned environment, a pre-planned map for the environment he is navigating into. So that's for the third category. For the fourth category, we have 3D sound systems. These systems can have a lower cognitive load. They can translate the the visual information into 3D sound cues. However, these systems are more complex and have a computational resources higher than other devices. For the fifth category, is the most common category, is the smartphone-based solution. This, we can have an app on the smartphone that can assist the users in their everyday tasks, in their navigation. However, these solutions are more limited to the resources of the smartphone, the computational resources of the smartphone. We cannot implement a lot of AI models and some features. It cannot be implemented in these solutions. So our solution or our methodology will combine or have a hybrid approach for all of the previous categories. We introduce Basir. This is the name of our device. We have a hybrid approach that combines computer vision, combines the 3D sound systems to provide a richer experience for visually impaired users. So basically, we have a camera that takes an input from the visual scene and have also a deep learning model that estimates the depth of the objects in the scene. For the sound part, we convert this information, the visual information about the objects and the 3D position information about the objects into a 3D sound cues. So if I have an object in that direction, I can hear it from the same direction, from the same way in the 3D sound outputs. We are overcoming the limitations of the work in the previous literature by performing real-time in our application and also not relying on internet connectivity and have much lightweight resources to use. Okay. So basically, we are introducing our pipeline. We have 2 separate pipelines. We have vision pipeline and a sound pipeline. So basically, our first input is monocular camera, and our final output is the spatial audio. So for the vision inputs, we are here having a main problem. The main problem here in navigation specifically is that the user are surrounded by a lot of objects, a lot of distractions. We are not interested in all of this information. So we must eliminate unnecessary information. So what is the necessary information we need? We need dynamic objects or dynamic information. That means we need moving objects. We need new objects that comes to the scene by sudden. So we are not interested in static objects or objects that already introduced in the previous frames. So we are selecting frames from the camera input and do what called frame differencing and motion detection. So we are masking the region area of the dynamic objects and the dynamic information, so we can use 3D understanding section to these regions only. That makes it more real-time performance and more lightweight to perform. So after having our masked images with the only interesting information we are needing, we are applying two different things, two different steps. So as we said, we are selecting frames and doing some basic frame processing, and this is the output. As you see, we are having here a car that is moving, and in the final mask, we are having only the car, and also there is a pedestrian moving, and it's shown in the image. For the next steps, we are taking the mask and apply it to the image and extracting the depth information. So basically, we can use stereo cameras. Stereo cameras can have depth information, more accurate depth information of the scene, but it can have more complexity, more computational resources. And we are not actually interested in the exact location of objects. We are only interested in the relative distance, in the relative location of the objects. So I'm interested in knowing that this object is much closer than the other objects in the same direction. So we are using a deep learning model that estimates the depth of the objects. We are using here MobileNet version 2 that reported higher performance in our embedded hardware that we'll be introducing in the next slides. Okay, after generating the depth map, we are using object detection models to extract the class names of the objects in the surrounding. So we are having, as we said, the depth information, we are having the object information. So it's time to convert this visual information into sound cues. So basically, we are storing the output in a log that will be used later in the sound pipeline. For the sound spatial audio pipeline, we are grouping, of course, the objects that are has the same name and has the same location in one class. So we don't have duplicated objects. And then we are doing two parallel steps. The first step is speech synthesis. We are converting the class names of the objects into a speech sound. We are having already translated or sound files of the class names of our object detection model. So we have 91 categories, we have 91 sound files in the cache, stored in the cache, that can be called anytime the user faces an object. And then for the position information, for the 3D position information, we are using head-related transfer function. That means if we are having an object, its name and its 3D position information, we are taking them as an input to the head-related transfer function. And as an output, the head-related transfer function maps the audio sound to the sound space according to its 3D position information. And finally, volume mapping. So we are having objects in different directions, but we need to be aware of its distance to the user. So we are mapping the volume of the object sound files according to the depth information. So if I have an object is more closer than another object, I will be hearing a louder sound for the object that is much closer than the other object, which will be a lower volume. That's for the volume mapping. Finally, we are mixing all these audio outputs into one stream file, so it can work parallelly when user navigate in the environment. Okay, for our performance and validation, we used our embedded hardware in NVIDIA Jetson Nano. We reported from 15 to 92 frames per second at a 10 watt power consumption. We tested our hardware on participants that are actually blind or visually impaired to see their user experience and the efficiency of the results. So basically, we applied our approach in an urban environment while we're seeing moving objects, and this is the mask of the selected objects that are moving. And for the sound, okay, this is for vision output. We are having objects that have class names, that have the 3D position information in the scene, and we are taking this information to the sound pipeline to sound that like that figure. So if I have an object to the left and one object to the right, and two objects to the right, I will be hearing the object names or sound files from the same direction it actually exists in the image. Okay. So for our technical performance testing, we compared our results to smartphone-based solutions and GPU-based solutions. We achieved a higher processing speed than smartphone-based solution and lower than the GPU-based. However, we achieved these results at a lower power consumption than the GPU-based. For the audio output, as we said, we are the only approach that are using 3D spatial audio. The other solutions are using only stereo output. That means that our experience for the user is much richer and have a lower cognitive load. So the user can handle different objects and different locations without being distracted by the sounds. Okay, so to summarize our contribution, we have achieved real-time performance on our approach that are not present in many solutions we saw in the literature review. We have applied our approach without dependence on internet connectivity, and also we achieved real-time results with lightweight models and more simpler solution. We experienced some limitations. For the object categories, we are only limited to the categories that are presented by the object detection model, and also for the lighting conditions, we experienced a lower accuracy in depth estimation for low light conditions. However, it can be solved by using high quality cameras and also enhancing and fine-tuning the object detection model by implementing a much classes. That's for our future work. And finally, we are doing a quantitative assessment to measure the efficiency of this assistive solution to a much wider sector of visually impaired individuals. And that's for all, and thank you.